Around about the time that I came into the possession of the oscilloscope, recovered from a school lab, I also came into possession of a function generator from the same source. And who watches the watcher? I mean, who's in charge here? Does the oscilloscope get calibrated by the function generator or vice versa? I really don't know. I'm not sure that I would trust this function generator actually for a couple of reasons. One is it's got, this is a seized component here, it doesn't work. I'm presuming it's probably voltage, and the fine adjustment for, I'm guessing the frequency doesn't work either. When I say it doesn't work, I mean you can't literally turn it. One of the things that I want to do is to try and free these up and have a look what's inside. So we'll do that. But the first thing to find out is, does it work? So if I power it on and stand back. Okay. So hopefully you can see that says 597. I'm having a bit of trouble picking up the camera. So what I might do is put a bit of red tape on there, and we'll come back and see if you can see it any better. Just one moment. Maybe you can see that a bit better. It says 597. To me, it doesn't seem to be flickering too much looking through the camera. It's pretty easy on the eye as well, so I'd say that's probably going to be okay. And what I've done is I've connected up the ground and output to channel 2 here, which I haven't used much before, so that's another bit of an experiment. But let's turn on the oscilloscope and see if we're getting anything from that channel. And yeah, okay. Hopefully you can see that. I'm seeing something slightly different on the screen as what I can through the camera because of the frame rate of the camera, but it looks like, well, this says square wave that it should be producing. I think if we have a bit of a fiddle with that, let's up the voltage first. Oh, it's channel 1. Yeah, and a bit of muscle memory there. Okay, so that's going to be pretty decent. And then if we change the time per division, bit of a noisy signal. That's not bad though, I guess. I guess that's a bit of a good square wave. Let's let's have a look at this and see if we can maybe figure out. It says it's at around 600, I don't know watts. It does say that the range is ×1, so maybe that's 600 hertz, I guess. But yeah, pretty noisy signal. Can't say I'm too happy about it. Mind you, having said that, both are pretty old pieces of equipment. I haven't cleaned these at all. The terminal, so I could probably do that. That might help a little bit, and I might do that when I open it up. What else can we do? I guess we could measure it. So I'm at 0.2. Let's go to 0.1, and if we change the position here, we can see that we've got one complete cycle in 1, 2, 3, 4, 5 divisions, and it's 0.1 milliseconds per division. So let's see what that's. I'll just get my little calculator out. So 5 times 5 divisions times 0.1, and it's milliseconds. So that's times 0.001. So we end up with 0.00, just see if we can see that on the, I'm just doing it on the little calculator here, 0.0005. So then we go 1 divide by 0.0005. It should read a frequency of, can we read that? 2000 hertz, and it says 600 hertz. Okay, that's nice. So yeah, well, look, I don't know. I actually would trust this as opposed to that. But one of the things I guess we could see is, can we get the other waves in there, and can we change the frequency? So this fine adjustment is locked, but let's have a look at the course. Yeah, nice. So we can see that that's gone up, and you can see also that the square wave has reacted accordingly. So it's contracting there as the frequency goes up. So that's good. It's got it's got some potential, I guess. Can it produce a triangle wave? Let's have a look. Oh, that's nice. Yeah, a little messy, a little Lionel Messi there, but yeah, jumping around a little bit. I mean, one of the things. Oh, that's an awful sine wave. Yucks. Quite attenuated down the bottom here, if that's the right word. I don't know if I can clean that up at all. Oh, it's very ugly. It is very ugly. Yeah, ouch. If a student drew a sine wave like that, I'd be definitely taking marks off. So, let's go back to the square wave, because that's not hurting my eyes so much. I think the next thing to do is to open this one up and to maybe try and free those rotating knobs. There's a couple of things that I don't really know what they do. There's a little switch on the back which I'll just flick. So I'm not sure. That went to 1900 brief. It's settling down. I'm not sure what that does. It's coming back to the same frequency on the display, but clearly this has changed. I wonder if that's worth. See if I can track that down. Oh no, that is a mess. That's a mess. Anything you'd use that for is a special effect in a science fiction movie, I think. So I don't know what that switch at the back does. It's not marked. Doesn't help. But yeah. All right, let's open it up and have a look. Okie dokie. I've just sprayed a little bit of WD-40 in these old bolts here, because I'm guessing that this thing hasn't been probably opened up since inception. Okay. Wow. So not too much that I can probably identify for you here, except for there's some chips, obviously, which I'll dive in a little bit deeper. So there's some circuitry, obviously, to take it from AC to DC, which I won't be touching at all. And then we've got our function generators, some transistors down here. It looks like there's a couple of fine pots that you could probably use for calibrating during manufacture. And it's these guys which worry me the most. That's this one, which is so this fine one down the bottom here, which is stuck, and no, this fine one here. So this one is the one that's stuck, and this one is the one that's stuck. So we can maybe try and free those up as well. Let's get in a little bit closer to these chips though, and see if I can identify them. It looks like almost like a homemade rat's nest job too. A couple of the components are a little on the ancient side. There's some TO220 components here, which definitely look like they've got a little bit of rust associated with them. But yeah, that's an interesting single board, it looks like. Oh, there's one up here as well. So let's see if I can turn this around and we can have a look at it. Yeah, a couple of caps and some resistors. It might be a crystal in there, maybe, and maybe that's where the actual clock is coming from, because I would have expected to see a crystal, so maybe that's that board. But I'll pull that out and we'll have a closer look at it as well. So yeah, let's do that. So going around the circuit here, we've got the one that I thought was a crystal. It's got a metal sort of sheen to it. And each time I do this, I'll put up a picture over here and I'll try and put up something from the data sheet as well. But the one buried under here is a TL074CN, which is a JFET quad op amp. And then this one here, buried under there, is an HCF 40106. That is a Schmitt trigger. It's a hex Schmitt trigger, which we've actually used on the channel before. So love my Schmitt triggers. So yep, that's what that one is. This one here is a 4011 NAND gate, presumably 4 NAND gates for that one. This one here is a 4017 decade counter. So there's one here, and then hiding under here, there are 2 more. And we've certainly used 4017s before as well. This chip here is the MM74C926. So it's called a 4-digit counter. It's got some other bits and pieces in there. It's specifically for driving 7-segment displays. So that would be providing the numbers out the front of the unit. And then in place of a crystal, and I can't see a crystal anywhere, but there is a XR22006CP function generator. So this is the one that's doing all the hard work. And there's a couple of caps. There's 1, 2, 3. Looks like adjustable caps around it. Presumably, yeah, they're adjusted during manufacture to make sure everything is working. Anywho, what I'll get to do now is I'll try and free up these pots and put it all back together and see if it still works, because that would be nice. Well, here we are back, hopefully live, with the function generator. The oscilloscope is on. The probes are connected, so with some degree of trepidation. Okay. All right. Sine wave, 800, I'm presuming hertz, if the range says 1. The fine balance should be back again. Yeah, look at that. That's nice. So the bottom of that range is 780. And it's still a bit stiff. And the top of the range is 820. So that's pretty good. So somewhere in the middle should be, I just pointed them straight up after putting up a little bit of WD-40. How good is WD-40? Very, very good stuff. Don't get me started. But anyway, the other one, which I thought was voltage. So this is, what are we showing here? It's the wrong channel. That is 50 millivolts. So that is 0.1 of a volt. Let's see what. Oh, that's, yeah, okay. So maybe that needs some more WD-40. It is changing the amplitude, but it is all over the shop. But clearly that's what that is for. That is for the voltage. So now if we just wind that back, yeah, okay. Still a pretty dodgy signal. I don't think the frequency is accurate at all, but let's just do that calculation again. So if we look at 2 divisions and 0.1 microseconds per division, so that's 2 times 0.1, and then times what is that? Milliseconds, sorry, so 0.001 to get 0.0002. So 1 divided by 0.0002 equals, 5,000 hertz, not 800 hertz. I think that was the factor before we started all this as well. So either I'm not driving this properly, I haven't worked out what the mysterious button at the back does. Not much to the signal, something to the display. So that's interesting, jumping all over the place. But whether or not it's a problem with the function generator or the oscilloscope, my money's on the oscilloscope, but we'll maybe come back to that in another video. I'm going to call that the circuit working for this week, though. That was fun. See you next time.